Hi everyone, this video is about probability trees and relates to exercise 906. We have talked about probabilities before briefly, but now we're going to go into some more detail. So the general rule with a probability tree is to multiply across and add down. So multiplying across, that achieves finding the intersection of events A and B, and adding down is the union of a group of events A or B. So here's an example. A die is rolled 3 times and it's noted whether it lands on a 1 or not. Draw a tree diagram of the possible outcomes. So when you draw a tree diagram, we want to try and keep them generally neat and tidy, which can actually be a little bit tricky. They can end up getting quite messy. So if a die is rolled and it's going to be a 1 or not, it can be a 1 or not a 1. And you can do an apostrophe, remember, for not, or a line above it. So I would write those first and then put a dot around the middle and the branches of your tree. And what we do is we write the probability of those things happening on the branches. So it's got a 1 in 6 chance that it is a 1, and it's got a 5 on 6 chance that it's not a 1. That's the first roll. Remember, these are multi-stage events, and that's the first stage. Now, assuming it was a 1 the first time, the next time it can be a 1 or not a 1. So just over here somewhere, a 1 or not a 1. Write those first, then the branches. And that's what'll keep it neat and tidy. Assuming we didn't get a 1 first, this time we could get a 1 or not a 1. Draw the branches. Now we need to write these probabilities on. Notice these probabilities will always have to add to 1. Now this is not going to change. Rolling it a second time doesn't change the probability. There's still a 1 in 6 chance that it's a 1, a 5 in 6 that it's not a 1. And those probabilities add to 1. Down here again, 1 in 6 that it's a 1, 5 in 6 that it's not a 1. Okay, that's our second roll. Now a third roll, I'm just going to write things a little bit smaller to fit it all in. It could be a 1 or not a 1. There's those branches. This one could be a 1 or not a 1. So we are starting to get a little bit bunched up now. Generally that means these examples won't have too many events to them, or they can get really messy. This one, it's a 1 or it's not a 1. And the last one, a 1 or not a 1. And again, we need to write all those probabilities on. 1 in 6, 5 on 6, 1 in 6, 5 on 6, 1 on 6, 5 on 6. It is a bit more bunched up than I would like. If you're doing this in an exam, I would suggest using about half a page. Now, what we should do is write our sample space down in this column. So if you follow that top branch, it goes 1, 1, 1. So 1, 1, 1. So if we follow the second branch here, it's 1, 1, not 1. So 1, 1, not 1. This branch is 1, not 1, 1. So 1, not 1, 1. This one goes 1, not 1, not 1. This one here starts with not 1 and then 1, 1. This one's not 1, 1, not 1. Not 1, not 1, 1. Not 1, not 1, not 1. 1, 2, 3, 4, 5, 6, 7, 8 possibilities in our sample space. Now I've got some questions on this. What is the probability of rolling 3 1s? Now, remember the rule is you multiply across. So 3 1s is just this top one. So it's 1 on 6 times 1 on 6 times 1 on 6. Okay, multiply across. So probability of 1, 1, 1 equals 1 on 6 times 1 on 6 times 1 on 6, which equals 1 on 216. The probability of no ones. Well, no ones is just this bottom branch here, 5 on 6 times 5 on 6 times 5 on 6. Again, we're multiplying across. So the probability of not 1, not 1, not 1 is 5 on 6 cubed. and that's 125 on 216. Now this last question is a very, very common HSC style question. It says at least 1, 1. Okay, if we go back up here, then there's at least 1 here. There is at least 1 here. There's at least 1 there. 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 There is at least 1 there, but not there. So when it says at least 1, the easiest way to do it, I mean, there's 2 options. One is we could calculate each of these. We could multiply across for each one, and then we could add them all together, adding down. That's the hard way. The easiest way is actually to calculate this one. We know all of these probabilities have to add to 1, so everything except this one is just 1 minus this answer. So down here we would go the probability of at least 1, 1 equals 1 minus 125 on 216. So I'm in my head going 216 on 216. So that's 91 over 216. Okay, in example 2, we have 8 red, 5 blue and 7 green balls placed into a bag, and 2 are drawn without replacement. Draw a tree diagram to show possible outcomes. Okay, so the first one I could pull out could be red, it could be blue, or it could be green. So the camera does go a bit blurry when I turn away, when I put my hand under. So I'll just draw on those branches. Okay, and I'll write the probabilities on each branch. So altogether in the bag there are 20 balls, 8, 5 and 7. So red was 8 on 20. Now I'm not going to simplify that at this point, but we will need to simplify all our answers at the end. Blue was 5 on 20 and green was 7 on 20. Okay, now we draw the second one out. So again, it could be red, blue or green. So next to my red one here, I could have red, blue or green. Draw on those branches. If I chose blue the first time, the second one could still be red, blue or green. Branches on. And if I chose green the first time, the next one could still be red, blue or green. Now, writing these probabilities on is a little bit trickier. Originally, there were 8 red balls in the bag. On this first one, I've already pulled a red one out of the bag. So there are no longer 8 red ones in the bag, and there are no longer 20 in the bag. There are now 19 left in the bag, and 7 of those 19 are red. So that one would be 7 out of 19. Okay, assuming I chose a red the first time, then there will still be 5 blue in the bag because a blue one hasn't come out yet. So that one would be 5 on 19. Assuming I chose the red the first time, there are still 7 greens in the bag. So that one is 7 on 19. Now I'd suggest you pause the video here and try and fill in the rest of those branches yourself. Let's have a go. So I pulled out a blue the first time. There are still 8 red in the bag, so this one will be 8 out of 19. I pulled out a blue the first time, so there's now 1 less blue. There are now 4 blue in the bag. So there are 4 out of 19 balls still in the bag. I pulled out a blue the first time, so there are still 7 greens. So that is 7 out of 19. And lastly, down the bottom here, if I pulled out a green the first time, there are still 8 reds in the bag, so 8 out of 19. I pulled out green, so there are still 5 blues in the bag out of 19. Now, if I pulled out green the first time, there were 7 greens. There are now only 6 greens out of 19. And so our possible sample space on this top branch is red, red. On this branch, red, blue. On this branch, red, green. This branch is blue and then a red. This is blue and then a blue. This is blue and then a green. This is green and then red. Green and then blue. green and then green. Now we've got some questions at the bottom. What is the probability of choosing a red ball and a blue ball? So when it says a red ball and a blue ball, it could be this branch, red-blue, or it could be this branch, blue-red. And remember our rule, we multiply across, we add down. So let's multiply across for those two. So for this one, 8 on 20 times 5 on 19. So 8 on 20 times 5 on 19. And this one is 5 on 20 times 8 on 19. Okay, so then I just need to add those together because remember we multiply across and we add down. So I'll just do this down the bottom. We've got 8 on 20 times 5 on 19, plus another one of those, really, it's the same thing. Now if I put that all together, that's the same as 2 times 5 times 8 on 20 times 19. Now the cool thing here is a lot of this does simplify down. 2 5s are 10, so the 10 and the 20 can simplify down to just 1 over 2. So now the 8 over 2 can simplify down to 4. So the final answer is 4 on 19. So often you can actually get away with not using a calculator for these calculations. Okay, both red is just the top one. So just this one is both red. It's the only way you can get both red. That's 8 on 20 times 7 on 19. This one doesn't simplify quite so easily. So 8 on 20 times 7 on 19. So the 8 on 20 simplifies down. It goes down a little way, but I just want to take it slowly. So I'm going to do 4 on 10 because 10's a really easy number to multiply by. So it becomes 4 times 7 on 190. Now I'm just going to halve the 4 and the 190. So 2 times 7 is 14 over half of 190. Well, half of 180 is 90, so 95. So at least one red is this one, it's this one, it's this one, it's this one, it's that one. So that one's quite annoying really to calculate. Now there are some shortcuts here. Remember these three all add to 1. So if I go 8 on 20 times 7 on 19 plus 8 on 20 times 5 on 19 plus 8 on 20 times 7 on 19, that's the same. If I factorize that, these will become 1. So it's 8 on 20 times 1, and that gives you those three all in one go. I'll show you what I mean. So we're going to find a shortcut to calculate this easily. So it is 8 on 20 times 7 on 19 plus, sorry, let me adjust the camera so I don't need to hold it. 8 on 20 times 5 on 19 plus 8 on 20 times 7 on 19. Now that's those three. I'm also going to put these two on. So I've got 5 on 20 times 8 on 19, and I've got 7 on 20 times 8 on 19. So plus 5 on 20 times 8 on 19 plus 7 on 20 times 8 on 19. Now, of course, you can just put all that in your calculator, but, you know, I kind of enjoy dealing with the fractions, so let's do it. So 8 on 20, those terms there, 7 on 19 plus 5 on 19 plus 7 on 19, they all equal 1 like I said. So this is 8 on 20 times 1. Plus, now I did notice over here that these both have an 8 on 19. So I'm going to factor that out. 8 on 19 times 5 on 20 plus 7 on 20. So that's 8 on 20 plus, now over here, 5 and 7 is 12, so that's 12 on 20. So 8 times 12 over 19 times 20. At this point, I will just put it in my calculator. So 8 on 20 plus 8 times 12 in my numerator, 19 times 20 in my denominator. Final answer, I'm just going to write it over here, 62 over 95.